Okay, so let's continue. So before we get into the lecture, I think a couple of general points. So one, we have an anonymous Google form for your feedback after every lecture. So I did not receive a lot of feedback from the previous lecture. It's okay, but for example, last year there were like a lot of feedback right after week one. So I just want to remind you guys that like there is actually an option to give me anonymous feedback about the course. So there was one feedback now in the break that my English is a bit fast. So if you think I'm speaking a little bit faster, let me know so I can slow down. Like as I said in the beginning of the course, the goal is really not to cover the syllabus. So I want syllabus is what we define. Okay, so I'm just curious. Do a lot of you think that I'm speaking fast? Okay. Okay, so then see, if you don't want to say that to my face, then you have this anonymous form where you can go and say. So if a lot of you say, then I would know that, okay, I know I'm speaking fast, so probably I will try to be a little bit slow, okay? But the problem is when I am in the flow, naturally my speed increases, stop me. So even people in the chat, in the Zoom, so if you think I'm a little bit fast in my speaking, let me know. And I will try to consciously speak slow. Okay, so let's begin. So far in this course, we have seen two types of prediction problems, regression and classification. And we have seen one example algorithm for each, right? So we saw least squares for regression, but then we also reused least squares for classification. And we also saw a new nonlinear algorithm for classification, which is k-nearest neighbors, okay? Now, we are going to go back to regression, okay? So probably we are going to do regression for a couple of lectures, to get even more deeper into the solutions. Then the rest of the course is just about classification. So for now, let's do a little bit more of regression. Okay, so far we have seen linear model for regression, right? So linear models for regression, and the simplest model that we have seen is linear regression, okay, which is basically y hat of x given w is equal to w0 plus w1 x1 plus wp xp, right? So why do we call this as a linear model? Because this is linear with respect to the parameters. And how many features are there in this example? P features, right? So the number of features is there are p features. Okay, now we have already seen that linear models are limited in performance when compared to nonlinear models. Our k-nearest neighbor example shows that, right? So now the big limitation of this linear model is this is also a linear function of the features x1 to xp, right? So now any system has input x, okay, but it also has some parameters w, and it combines the input and output to make the output y, right? So nonlinear models will have some nonlinear function of its parameters, okay? However, there is a cheap trick that we can do to get nonlinear solutions. We have already seen one example of it, which is the polynomial regression that we have seen, right? So the cheap trick is instead of making the parameters nonlinear, you can actually make the input nonlinear, okay? Then when you combine these things, you still get a nonlinear output, right? This trick has an advantage. The advantage is you're still dealing with linear models where we have closed form solutions, but you get a nonlinear boundary for free, right? So the limitation of simple linear model is that it just is a linear function. Limitation is Okay, first of all, maybe I'll tell you the advantage. The advantage of linear model is you have closed form solution, right? It's very efficient to implement. However, the disadvantage is it is also a linear function of input. Okay, now, so this is where we're going to define our next class of models, like which is linear basis function models. Okay, so what are linear basis function models? These models are going to take the input and construct some non-linear basis functions. Okay, you take x and construct some function out of it, x square, x cube, x power 4, and so on. Okay, let's just call these functions as like phi. Okay, so now y hat of x comma w is equal to w0 plus summation j is equal to 1 to m minus 1 wj phi j of x. Okay, I have constructed m minus 1 basis functions. So phi j of x are called as basis functions. Okay, so these are normally a fixed nonlinear function. Okay, now for example, if you want to do the polynomial example, I could have one basis function like phi 1 of x could be just x. I could have another basis function phi 2 of x, which is x squared. I can have another basis function phi 3 of x, which is x cubed. Okay, now as you can see, this x square x cube trick is just one possible trick, right? You can do whatever nonlinearity that you want. And we are going to see some nonlinearities today. Okay, now I can also assume that phi 0 of x is equal to 1, so that I can put everything together. So summation over j is equal to 0 to m minus 1 wj phi j of x, or in other words, w transpose phi of x. Okay, where w is the vector that we already know, w0 to wm minus 1, right? Now we have this new phi vector, which is phi 0 to phi m minus 1. Is that clear? Now, this function, is this a linear model? It is still linear because it's linear with respect to the parameters, right? Like, so it's just a linear combination of wj's. However, can it model nonlinear functions? Yes, because inputs come in nonlinear fashion, right? Now, let's see some example basis functions. Oh, no, what did I do? Okay. Let's see some example basis functions. Okay, so I moved things too fast, so the video should resolve itself. Let's just give it 10 seconds. Okay, so the first, come on. Okay, so the first basis function that we are going to see is something that we have already seen, the polynomial basis function. Okay, now the polynomial basis function is phi j of x is equal to x power j. Right? So you can just add as many basis functions as you want. That is going to be the degree of the polynomial. Okay. Okay, so the video is still not resolved. Usually it resolves by itself. Yeah. Okay, so now the second, there are many other possible basis functions. Okay, so we are going to see a few more examples. So the second basis function that we are going to see is Gaussian basis function. Okay, where phi j of x is going to be x of minus x minus mu j square divided by 2s square. Okay, now this mu j's, right? So they give the location of these basis function, and yes, similar to the standard deviation in Gaussian, is going to give you the scale of the basis function. Okay, now there are several important points here. Okay, first of all, this doesn't have any probabilistic interpretation. Okay, so I'm just using the word Gaussian in the basis function because it looks like a Gaussian. Okay, you can see that there is no denominator normalizing the distribution here. So that's because anyway we are going to multiply this basis function with a linear value w, right? So this is not probabilistic. Okay, this is just looking like a Gaussian. Second of all, can someone tell me what are these mu's and yes? So how do I find these mu's and yes? Who gives me these mu's and yes?
The hyperparameter?
Yes. So these are hyperparameters of this basis function. Okay. You decide a bunch of random mu's and yes, and that forms your basis function. Okay. We are not learning mu's and yes. Okay. So one important thing to remember is the basis functions are not learned. They are often fixed. Okay. As usual, we are going to make things general and general. Like so, in the future, we will see how to learn these basis functions. But for now, these basis functions are fixed. Somebody gives you mu's and s's, like as hyperparameters, and you're going to construct these basis functions. Is that clear? Okay. Now we'll see one more basis function, which is sigmoidal basis function. Okay. As the name suggests, it's going to look like a sigmoid function. So phi j of x is equal to sigma of x minus mu j by s, where again mu is the location, s is the variance, and sigma of x a is defined as 1 by 1 plus e power minus a. So this is like the logistic sigmoid function. Okay. Now, finally, one can also think of a very simple basis function, identity basis function. Okay, which is phi of x is equal to x. If I use identity basis function, then I recover the linear regression model. I'm not doing any nonlinearities. Is that clear? Now let's see how these basis function would look like. So here you can see the polynomial basis function. Okay, so for different degrees of polynomial, when your degree is 0 or 1, is it 1 the linear? When degree is 1, I think it's linear. Okay, so you have like degree 1, degree 2 is your parabola, then degree 3, degree 4, and so on. Okay, so depending on which degree you are using, you're going to get that basis function. Now you combine a bunch of this, then you can get any curve that you want. Similarly, these are your Gaussian basis functions. Like you combine a bunch of them, you're going to get a nonlinear function. Sigmoidal basis functions. Okay, is that clear? Okay, so now we have already progressed from what we were using in the last lecture, right? Like so, in the last lecture we focused just on linear models. So now we are still in the linear model setting, but we can already get nonlinear output by using these basis functions. Okay. Now the rest of the theory doesn't change. Least squares is just least squares. Okay. We are going to quickly go through it. So least squares with nonlinear basis functions. Okay. So the least square error, right? The E of W is given by y minus phi W transpose y minus phi W. Okay. And I think you have 1 over 2n, like in the left side, right? Like so, 1 over 2n. Okay. Now W star is given by R min of W, E of W, right? Like whatever W that minimizes this E of W. Now the W star is given by phi transpose phi inverse phi transpose y. If you remember, our solution for the least like linear regression was x transpose x inverse x transpose y. We are just replacing the x with the nonlinear basis functions. That's it. Okay. Now, I think we have already discussed this. So this, right? So this has a special name in linear algebra. So we are going to call this as phi plus or phi plus. So phi plus is basically phi transpose phi inverse phi transpose. This is known as Moore-Penrose pseudo inverse. Okay. A quick note: if phi is square matrix and invertible, okay, then phi transpose, like phi plus is actually equivalent to phi inverse. Okay, but in most of the real life applications, it is not a square matrix, and sometimes it's also not invertible. So that's when you are using the pseudo inverse. Okay. Okay. So now let's try to okay. So we'll pause here about like basis functions. Okay, and we are going to try to understand a bit about the geometry of least squares. Okay. So what exactly is this least square solution, right? Like, so can we characterize it by visualizing things? Okay. So we are going to start with a very simple setting, and then I will generalize. Okay. So now consider I have only 3 examples. Very easy. Okay. So just 3 examples, and I have 2 features. Let's just call them as phi1 and phi2. Okay. Is it clear? Now, when I have 2 examples, how would my linear regression look like? So my linear regression is basically W. For the moment, let's forget about bias. Okay, there's no bias here, but everything holds even if there is bias. So you have W1 phi1 plus W2 phi2, right? Now you have these 2 vectors phi1 and phi2. Now let's assume that these are the 2 vectors. This is phi1 and this is phi2. Okay. Now when you have 3 examples, you are in a 3-dimensional space in terms of y, right? However, these 2 vectors, and since you are doing a linear combination of these 2 vectors, my y hat, right, can only lie in the subspace spanned by these two vectors, right? Like, so let's say this is all possible combinations of phi1 and phi1 and phi2. Okay. Now, my y hat is just a linear combination of these 2, right? So it is going to be, it could be either this, or it could be this, or it could be this. Okay. However, my y vector, right, the output that I'm looking for, since there are 3 examples, this is a 3-dimensional vector, right? Like, so now in the 3D space, let's say something like this. Okay. Now, my phi1 and phi2 can only cover one plane, right? So it is very possible, like in fact, like it's highly probable that this y vector will not lie in this plane, right? Like it's a 3-dimensional space. Imagine a 3-dimensional space where you just have one plane, which is what your solution space is. Now you are interested in finding one of the solutions among these many candidates, which is as close as possible to the actual y vector. Okay. Now let us say the actual y vector is something like this. It comes out of this space. Okay. Now linear regression cannot achieve this solution. On the other hand, what it can achieve is something like this. Okay, such that the distance between y hat and y is as close as possible. Is that clear? Okay. Now, for people who have not seen geometry on vector spaces for a long time, like this might be a little bit difficult. Okay. So I'm going to repeat this. We are considering 3 examples, which means I have y for first example, y for second example, and y for third example, right? So it's a 3D vector. Now this vector is lying in a 3D space. It could be anywhere. Like, so for example, this could be my y vector. Okay. So however, I have only 2 features. 2 features cannot represent a 3D space. two features can only represent a 2D space, right? Now, just for simplicity, let us say that the two features can only represent this 2D space. Okay. Now that means I can only find a line in this space and minimize the error or distance from that line to the y as close as possible. Now, can someone tell me what that y hat would be in this example? So in this example, like you can see that this is my solution space, like a plane, and this is my y vector. I want to find a y hat which is as close as possible to y from this subspace. So how would you find that space? Like how would you find that vector?
Maybe with the projection?
Yeah, it is just like what kind of projection? It is just the orthogonal projection of this y vector, okay? So you project this y vector like this to the space, and this line is the best y hat, okay? Or in other words, least squares corresponds to the orthogonal projection of y to the subspace S created by the features. Okay, I'm going to summarize it. So the least squares solution corresponds to orthogonal projection of y onto the subspace S created by the basis functions. Okay. Any questions? Any questions in the chat? No. Okay, so somebody says yes. Is there a question? Okay, so Joseph, can you raise your hand? Let me see if I can make you speak. Okay, can you raise hand? Okay, maybe, okay, I'm asking you to unmute. You can unmute yourself.
Hello?
Yep.
You can hear me well?
Yes.
So I was wondering about the link between the three examples,
Okay.
because you created a space with the three examples, but they could be like linearly dependent. For example, y3 could be a linear combination of y1 and y2.
Okay, so we are not talking about features. Y's are your predictions.
Okay.
But I see your point. So your point is valid for features. Like, so what if phees are linear combinations of each other? Okay, so we are going to come to that very soon.
But I suppose they are orthogonal to each other if we're using them as a basis. The basis functions, they are yeah.
Yes, but if they are not orthogonal, if there is any dependency, then we have issues. We will talk about it.
Okay. Okay.
Okay. Can you mute yourself? Okay. Yeah. So any other questions? Okay. So then maybe let's talk about the issue that he mentioned, right? Like, so there are few issues with the current setup of linear regression. Okay. So issues. So the first issue is if the columns are not linearly independent, okay, like let's say I have some bunch of features, okay, if the features or basis functions, whatever, are not linearly independent, okay, so then X is not full rank. Like for example, let's say there are two input features which are perfectly correlated. Let's say X2 is basically 3 times X1. Okay. So one example I can think of is like in a lot of forms, they ask you both age and date of birth. Now, age and date of birth are perfectly correlated, right? So there is a correlation. So when you have these correlated features, then X transpose X is singular. Okay, which means W star is not uniquely defined. how would you solve this issue? How would you solve this issue? Yeah.
We can just remove one of the features.
Remove the redundant features. Okay. So again, like we will not talk about data preprocessing in this course, like, but the answer is you remove some redundant features, which means you normally do some feature preprocessing. Okay. So in the future, like we're going to have a tutorial on scikit-learn. So where I think TAs will briefly touch upon different preprocessing options that are available in scikit-learn. Okay, so the solution is filter redundant features. Okay, now the second issue is we can have rank deficiencies when the number of input features P exceed the number of data points. Okay, so this is not a very normal scenario, because often we have a lot of data, right? But there are some times when input features, the number of input features P is greater than the number of examples N. Okay. Now in this case, you're going to have rank deficiency, and hence you'll have the problems like before. So now how would you solve this problem? How would you solve this problem? Okay, so there is one solution in one answer in the chat, which is remove some features. Okay, you can do feature reduction. Anything else? We have already seen some solution, yeah?
Get more examples.
Okay, let's say you can't get more examples. We have seen another solution.
Regularization.
Regularization, right? You can add regularization. Okay. Okay, so okay, so we'll have like one small like discussion about how to extend this to multiple output scenarios. Okay, and before moving to the next topic. So the point we are going to discuss now is like what happens if there are multiple outputs. So far, we assume that you are going to predict only one real value, right? But there might be applications where you are predicting more than one real value. Like, so for example, let's say you are interested in predicting XY coordinates in something, okay? So in this case, you have two real values, X and Y. And you might have some problems where like you're predicting, let's say, the temperature, humidity, and a bunch of things. Like you're predicting them, they're not features, okay? So you could have these prediction problems where you're interested in predicting not just one output, but many outputs, right? So now, in this case, Y is a vector. If there are K things to predict, then Y belongs to R power K. Okay? Now, how to modify our linear regression solution for more than one output? Any ideas? So how would you approach a K output regression problem?
Can we split them into K different problems where we get one single value?
Okay, so that is the naive solution, right? Like, so solution one is to treat them as K independent regression problems. Okay, which means you're going to have K different basis functions and you construct phi transpose phi inverse phi transpose x or y solution for these k different problems, right? So now is there something that, like, can we do better than that? So this is an obvious solution, like you have to do k separate regression problems, but can you make use of the fact that there is only one input and you're using this one input to do k different predictions? So there is a better solution here, okay? So the better solution is to use same set of basis functions to model all components of y hat, okay? Or in other words, my y hat of x comma w, okay? Remember this is a vector now, it's not a scalar, is going to be capital W transpose phi of x. Phi of x is my basis data matrix, right? So based on the basis function. If you remember, for one output scenarios, we had small w transpose phi of x, where this w was a vector, okay? Now you have k different such vectors for k independent problems. You put them together into a matrix, okay? Now this w, right, is a m cross k matrix. There are k m-dimensional vectors, okay? Now, the beauty of this solution is our previous least square solution holds exactly. If you want, you can derive, but the W star, the parameter matrix instead of vector, is going to be phi transpose phi inverse phi transpose capital Y. Okay? Previously, this Y was a scalar, now it is a vector. That's the only difference. Okay? So, it's a neat solution. So Y here is basically a n cross k target vector. Now, if you look at the individual solutions, okay, what would be the kth parameter vector for the kth prediction problem, right? Like that is going to be phi transpose phi inverse. Oh, sorry. Phi transpose phi inverse. Okay, phi transpose phi inverse phi transpose yk. Okay, so in some sense, it naturally decouples into k different problems. But the big advantage here is you compute this pseudo inverse only once, and then you use it for all the k problems. Is that clear? Will you be able to implement a regression for k output problem now? Okay, so any questions so far? Okay, well, if there are no more questions, we are going to see our first learning algorithm. Okay, so far in the first in the linear regression case, we had a closed form solution. You don't need to learn anything, right? Like, so the solution is given, and in k nearest neighbor there was no learning, right? Like, so you just store the examples and you get to make predictions based on the example, right? Like, so now we are going to probably see not just the first but the most prominent learning algorithm that you will see repeatedly throughout the course, which is basically the idea of gradient descent. Okay, so we are going to discuss how to learn by gradient descent. Okay, now let's consider a very simple regression problem to explain gradient descent. Okay, I have one input feature x, okay, and I have just one output feature y. Now we are going to do linear regression, okay, which means y hat of x given w is equal to w0 plus w1x. Okay, now what are the parameters of this model? It is just w, right? So w0 and w1. Now, what is the loss function? I know I'm repeating this again and again. The hope is that you will internalize it. So the loss function here is a function of w0 and w1. okay, which is basically 1 over 2n, summation over I is equal to 1 to capital N, y hat of xi w minus y of I, the whole square, right? So the goal here is to minimize L of W0, W1 with respect to W0, W1, right? Now, in the case of this specific linear regression example, we know that this is a quadratic loss function. So whenever you have a quadratic loss function, you can differentiate it to 0. You are going to get the closed form solution, right? However, moving forward, we are going to see nonlinear models where we are going to have nonlinear loss functions. So when you have a nonlinear loss function, which is higher than quadratic, right? So then you cannot easily differentiate, set it to 0 and find the closed form solution. Often, for a lot of interesting models, closed form solutions doesn't exist. Okay. Now, our first option is out, right? Like, so now how do we find W0, W1? Okay. So for this discussion, let us assume that we don't have the closed form solution option for linear regression. Now, how do I find W0 and W1? Okay. So now this is where the idea of gradient descent comes in. Okay. So to understand the idea, let us try to visualize the loss function and how it looks like. Okay. So here, you see what I have done here is I have just considered different possible values of W0 and W1. Okay, the model here is W0 plus W1x. Okay, I consider different possible W0, W1, and I construct, like I compute the training loss. What, for example, what if I set W0 and W1 to be minus 10 and minus 10? Okay, then I get a loss, right? So I'm going to plot all these loss functions. Okay, now this is basically the loss surface for the model, for our loss function. Okay, now what do you learn or what do you understand about this loss function? So we are interested in finding the minimum of this loss function, right? So yeah, you had something to say?
Yeah. So about this, actually, the minimum is in the center.
The minimum is?
Like in the center, there's the curvature, and like it depends on just you can start in one direction.
Okay, so anyone else? Yeah.
The derivative of 0.
Yeah, so we know that the minimum is when the derivative is equal to 0. But like, what do you see from this loss function visualization that we did not know before? Or maybe we knew it before. So this is actually a quadratic error function, right? Sorry? There's only one minimum, right? So we know that this is a quadratic function. So we know that there's only one minimum. And we kind of verify that with this last surface. You can see that this is a nice bowl with just one minimum. Okay. Now, that means that imagine I put you inside this loss function, okay, with your eyes like blindfolded. So you are blindfolded and you are standing here, and I want you to find the minimum. So how would you reach minimum? Sorry? Okay, but you are blindfolded, so how would you know that you are going down?
If you put yourself.
Okay, so if I put you in this region blindfolded, like, so what you would try to do is like you would just use your leg to see like where is the slope, right? So you'll see where is like a descending slope, and you'll take some step, right? Like, so now the beauty of this loss surface is it doesn't matter where you start, right? Like, so you could start here or you could start here. You take these tiny steps towards the negative slope, you are going to eventually reach the minimum, right? Now, that is the idea behind gradient descent, okay? So I'm going to first give you an outline of the algorithm. We are going to make it more formal. So gradient descent, outline. So you start with some W0, W1, any random W0 and W1, okay? Then you keep changing W0, W1 to reduce loss of W0, W1 until we hopefully end up at a minimum, okay? So every time you use your legs to find which is the negative slope, which means the loss is low there, right? Like so the simple way to do that is like you are in one particular point, okay? Let's say here, you try different combinations in the neighborhood. Whatever combination has the lowest loss, you take that step, okay? But this is a very naive way. We are going to see much more elegant way of doing that very soon. But this is the idea, okay? So now, can we formalize this mathematically so that it becomes a precise algorithm to implement, okay? So this is what the algorithm would look like, okay? So I'm going to repeat this process until convergence, okay? The process is very simple. Wj is equal to Wj minus alpha times dou by dou Wj of the loss function. Okay, and you are simultaneously updating for j is equal to 0 and j is equal to 1. Okay, so what am I doing here? So first, I'm computing the derivative of the loss with respect to my parameter. Okay, so that is going to tell me the slope, but it tells me the positive slope, so I should take step to the opposite of that. So that's why I have the minus symbol here, okay? And I don't want to take big steps. I want to be conservative, right? Like, so imagine like you're blindfolded and you're taking steps. You want to take tiny steps, right? Like you don't want to take a big step and fall down, right? So that is controlled by this alpha, okay? So alpha is step size, or also known as the learning rate of the gradient descent algorithm, okay? Now, imagine this is my loss function, okay? Instead of the 3D, we have a 2D version here. Now, if you start here, if you take very small steps, you're going to go very slowly, like this. It will take you a lot of time to converge, okay? So if alpha is too small, you're going to converge very slowly. However, if alpha is too big, if alpha is too large, right? So you're here, you take a very big step and you miss the minimum. So you could actually go here. From here, you take a big step, you go here, you could actually diverge. Okay, so well, probably this was a bad example, so I'm going to remove this. Let's say you start here, okay? You take a very big step. Instead of reaching here, you reached here. Now you complete the gradient, you take another big step. You reach here, you reach here, you reach here, okay? So basically, gradient descent can diverge if alpha is too large. Now, what is alpha? How do I pick alpha? Right, so when I say how do I pick alpha, it means that alpha is a hyperparameter, right? Like so, this alpha is a hyperparameter of gradient descent. Okay. Now remember, your model itself will have some hyperparameters. Like for example, if you're using a polynomial regression model, m is a hyperparameter. Now on the top of that, you have another hyperparameter which is introduced by gradient descent, which is alpha. Okay. So this alpha is probably the most important hyperparameter that you will see in this course. Okay. So learning rate is the most important as well as most sensitive hyperparameter, and it is very, very important that you tune your learning rate very well. Okay, so we are going to explore a lot of this in your practical assignments. Now, I want to give you a very quick note that as you go closer and closer to the optimum, your gradients are going to shrink. right? So the magnitude of the gradients are going to shrink, right? So you don't need to play with alpha. You don't need to change the value of alpha when you're doing gradient descent. You can have fixed alpha. The gradients are automatically going to shrink, so steps are going to be automatically shrinked. Because your step is not just decided by alpha, it is also decided by the magnitude of the gradient. So the gradient is already small, your steps are also getting small. So when you reach the minimum, your gradient is 0, so you don't take any steps, okay? So any questions about gradient descent? Yep.
Is it the direction of the vector independent of alpha? Like how can it go down and then go back up if the derivative is the good side?
Oh, so this is when you are overshooting. So if alpha is too large, let's say like you can take a step like this. This is where the minimum is, okay? But if your step is too big, then you, okay. So if your step is too big, then you, from this x, you jump to this x, okay? Then from this x, you jump to this x. So when you go to that x, the corresponding loss is very high. Any other questions? It's very, very important that you understand how gradient descent works, yeah?
What we use when we have multiple minimums and we don't know which one we get how to find them.
Okay, we will talk about that. That's what I wanted to talk next, but probably we will do that in the next lecture. Before I finish, I just want to give you a solid algorithm for linear regression using gradient descent because you are going to implement it today in your assignment. So linear regression and how to do gradient descent. Okay, so the loss function here is 1 over 2n summation over I is equal to 1 to capital N W0 plus W1 xi minus y of I. Right? Now, if I compute dou L with respect to dou W0, that is basically 1 over 2n summation over I is equal to 1 to capital N. So this is x square. So when I differentiate this, I get 2x, right? So 2 times x. X is basically the whole thing. W0 plus W1 xi, sorry, minus y of I. Okay? Then I have to differentiate inside by chain rule. So if I differentiate this with respect to W0, I get 1. Okay? Now similarly, dou L by dou W0 is given by, okay, this cancels. 2 over 2n summation over I is equal to 1 to capital N, W0 plus W1 xi minus y of I. Now I differentiate this term with respect to W1. What would be the answer? Huh?
W1.
No, I'm differentiating with respect to W1.
Just make sure you wrote the DL over the
Oh, W1, sorry, W1. Oh, sorry. Yeah. So what is the differentiation of this term with respect to W1?
X.
Xi, right? So multiplied by Xi. Okay. Now my gradient descent algorithm is going to look something like this. You repeat until convergence. Okay. W0 is equal to W0 minus alpha times 1 over n summation over I is equal to 1 to capital N y hat of xi given W minus y of I. Okay. And W1 is equal to W1 minus alpha times 1 over n summation I is equal to 1 to capital N y hat of xi minus, sorry, xi given W minus y of I. That's it. Okay. So I think I have done well in terms of coverage, even though I had an ambitious goal of finishing this whole thing today. So tomorrow, like in the next week, so we're going to discuss more about gradient descent, and we will also talk about regularization again. Okay. So we will stop here. Again, as a reminder, finish your A0 submission today, and assignment 1 will be released tonight. You can start working on assignment 1. So we have seen enough concepts for you to do at least half of the assignment. So by next week, we will finish everything for assignment 1. But don't wait till next week. So start with your assignment today. I think we will stop here. And as usual, this is my office hour, so I'm going to stay here until somebody asks me to leave. Then you can come back. Come to my office. Okay, so for people in Zoom, I'm going to stop the call.